I'm the Press and Media Officer at ETSI and your moderator today. This webinar offers an overview of the recently announced ETSI Open Source MANO Release 13 and a demonstration of some of its latest features. Our presenters today are Francisco Javier Ramón Salguero from Telefónica. He's also the chair of OSM. Gerardo García de Blas from Telefónica, chair of OSM Technical Steering Committee, and Mark Bayer from Canonical, a member of the OSM Technical Steering Committee. They will be followed by a Q&A session, should time allow. If you would like to ask a question, please click on the Ask a Question button and type it in. But before handing over to our presenters, I'd like to remind you of some quick points about our webinar today. A recording of this webinar will be available on demand a few minutes after we've ended it at the same location as where you are right now. So please feel free to ask questions by clicking on the question button. We'll handle a question at the end of the webinar. And don't worry, if we don't answer at this time, we'll get back to you after the webinar by email. The slides in PDF format have been provided in the attachments sections so that you can download them. Now, over to you, Francisco.
Thank you, Claire. Welcome to this OSM webinar on our new release, the Release 13. And as Claire said, we'd like to present you what are the main new features that come with this release, and also tell you more globally what are the kind of things that you can achieve with OSM, right? So for that purpose, we've prepared this agenda. On the one hand, we will, at first, for those who are newcomers to OSM, or are less familiar with what OSM can do and what is the size and reach of the OSM community, we'll give a brief overview. And later on, we'll demonstrate two of the new features that come in this new release. I mean, we can't demo all of them because we need a really long webinar just for illustrating each of them. But we have chosen two features that we believe that are representative of the advantages that come with the new release. Well, why OSM? I mean, the thing is that, I mean, the challenges for NFV orchestration in a telco cloud are growing, and we are growingly ambitious on what we are asking to our telco clouds. I mean, we have requirements for the new services. I mean, we have typically consider 5G services, IoT, edge services, broadband accesses of many kinds, all new innovative type of services that are coming and are promising, and the service providers want to try, and that those have different requirements, as you may imagine, and also there are, of course, business drivers. I mean, there are always the usual pressures. I mean, of cost reduction. That's one driver in any healthy business. But also a reduction of time to market. That's important because, I mean, in many of these services, time is money, right? And overall, you need to have an appropriate user experience, and you can your aim is to improve it, right? And you're playing with some constraints as well in that environment. On the one hand, we are now consolidating over those telco clouds existing workloads, more traditional workloads, together with network workloads, NFV-like workloads. You need to deal with legacy systems. They will not disappear overnight, right? And you need to be friendly with them in that telco cloud, and of course coexist with those initial vertical deployments that happen at early stages or NFV, and that are in your environment, but are not necessarily as horizontal and as multi-purpose as the new generation of telco clouds are providing. And all that in an environment where there is a continuous innovation in the technologies that are encapsulating and are hosting those workloads. So you have, of course, containers with Kubernetes as a start. You have a pressure of new type of hardware. You are always seeing the development of some technologies for autonomous operation and a variety of cloud technologies. All that is what makes the mix of next generation telco cloud. And how OSM can help there, right? The role of OSM in all this picture is being able of providing a platform that can create networks as a service in a manner that you are having network functions that are composed of many small components in your cloud, but you are playing the role of a sort of specialized platform as a service that is extended for network functions with a differentiator to traditional vanilla platform as a service that you have to deal with a very complex connectivity and also dealing with a special allocation of resources in the cloud with APA and underlying scenarios, and also solving the relations between different components that are supposed to be pluggable and work together in a network, right? What OSM provides is either a whole network service or simply a network function that is ready for their use, right? For its use, right? And exposing the function and its life cycle, right? So you don't need to handle anymore individual components, and you can interact with them via primitives. That's what OSM delivers, and that is what has been in the scope of OSM since its foundation, I would say. But obviously, with each release, with an additional refinement and incorporating new technologies. Here is very clear in this slide. I mean, we are incorporating gradually more type of technologies and infrastructures, and also being able to handle multiple sites with more ease, right? And we'll talk about that later, about the scalability challenges and hurdles that we overcome with the new technologies that we are incorporating in OSM, and well, that is one aspect, and the other is that we need to combine network functions that come in different formats and can have a combination of virtual machines, containers, or even physical assets that need to be connected to the virtual components in a given way, right? All that is supported by OSM, and it bundles them in a higher abstraction so you can manage them more conveniently. And autumn data plane workloads, of course, since also the beginning of OSM, there is a use case that is properly covered and is differential for network functions in comparison to traditional IT workloads. And the thing is that with all that we have commented, that would suffice for having a tool that helps you in that automation. But what is important is what you get in return is that OSM is able to create packages that are agnostic to the technology. So once you are able to encapsulate all those knowledge about how your services should be set up, is made in a cloud agnostic manner. So if you deploy it eventually in one cloud and you validate it end-to-end in that cloud, a given use case, the packages that you are producing, once that they are validated, you don't need that cloud anymore, and you can redeploy that based on that packages in completely different technologies and locations. That is the beauty of the modeling that you have, that you do once, but you repeat indefinitely in many locations, saving a lot of trial and error per location. So the automation comes from the beginning, right? So you see the benefits and also the independence, the detachment from the different cloud technologies. As a result, this will make your life easier. I mean, there will be a big reduction of complexity, as you can imagine, because you will be working with network functions or network services. The deployment in multiple locations will be as easy as has been described. The independence of the type of cloud minimizes the potential lock-ins and problems with specific technologies. Is vendor agnostic for the same reason. The testing, once that you're validating in one environment, you can rest assured that there are high chances that it will work with no changes in other places, minimizing also the errors. The time to market is for the second deployment, say, is minimal. And you can plan for more ambitious types of capacity growth among different clouds. If you want, you can move workloads even between clouds. The redundancy schemas come for free in this environment, and overall we are reducing effort, right? So I think that this is the most important outcome of any type of automation initiative. So this is not anything that happens by itself. This is the result of a community effort with a large community behind it. As you can see, players of all the parts of the industry, and also we are having a significant OSM ecosystem of commercial products that exist just because they are building or relating their products somehow to OSM and granting that they will work properly, right? So that is, I mean, that is the tip of the iceberg of the initiatives that are happening, but it's significant enough so we can understand the relevance that OSM has. Actually, one of the big sources of feedback and information is the own community of users of OSM that are big. I mean, the success of our releases is significant. I mean, there are a big number of installations per each of the releases, as you can see, and obviously with more relevance in the long-term support releases, as you may imagine. But as a result of that, and large community of users, we are taking seriously into account that feedback in field, so we can refine OSM and adapt it to the new needs as we create a new release, as we did in this one, right? Also, it's important to tell that there is a strong preference in the research community for using in their own projects OSM as the orchestration of choice, right? We are quite glad that is happening naturally, but as a result of that, there is a large benefit for OSM also, because we are seeing a lot of uses of OSM in challenging use cases and complex cases, and we are getting feedback out of them that probably in the most basic scenarios will not even dare to tread, right? And on the other hand, many of these research members are contributing back to OSM with improvements to the functionality of OSM. So we are really happy with seeing these synergies, and we'll keep exploring them in the next releases, as you may imagine. And here is the release. In this context is where Release 13 comes. Release 13 adds many new features as the new releases in OSM lately that are quite busy in terms of new features that are included. This one is not an exception. And many of them are sort of revolutionary features, and some of them are evolutionary, as unsurprisingly, based on the feedback and the lessons learned on what we are doing. We are having we are adding a new closed loop lifecycle architecture. This is important because, I mean, we understood that in the closed loop technologies that were embedded in previous releases of OSM, we might potentially hit in the future scenarios, not in the current scenarios, but in future scenarios, or the extreme decentralization, etc. We might hit some limitations in the amount of sizes of monitoring and feedback loop. So we were giving it a thought architecturally, and now we are incorporating in our release 13 a new architecture that can scale, I would not say indefinitely, but almost indefinitely, regardless the size of the deployment. So we are quite happy on this one. And the thing is that we'll describe this one in detail during this webinar with the first of the demos, so I will not extend too much. It will coexist with the traditional architecture that we have. So this will be for the time being an additional component to install optionally, right? And eventually the idea is that we could gradually switch from one framework to another. So when the time comes for massive decentralized deployments, we are well equipped for doing that transition. The internal evolution of the life cycle is important. This is mostly housekeeping and is only understandable for those who are using OSM. And we'll realize that now we are gradually getting more information and more granular feedback on the progress of the operations. This is not anything that will happen in one single release, because it's a granular. We are doing it step by step, so to say. But in every release, you will see benefits on this evolution, on this pattern that has been adopted in the internal lifecycle management of OSM. The execution environments, as part of one of the modalities of the E2 that OSM ships to allow the E2 operations, there are improvements in areas related to security mainly, and the internal communication channels and external communication channels. So now they are much stronger than they used to be, and also we can update more easily those management environments without making impact in the network function itself. And also we are improving the naming of the resources that are being deployed. Not necessarily something that you will realize immediately, but if you are doing troubleshooting, it will make your life easier. So that's why it was implemented in the case of the chance for the E2, right? Regarding the network service deployment, we have improved the way that we manage the persistent volumes of a VNF. This is different in the manner that we have more choices than we used to have. So now we can choose on whether we keep them or we remove them, or what to do with a persistent volume, because it may we store sensitive information that we want to keep. And we will have a demonstration later, so I will not extend much on that. Also, we are improving the security in the interaction with the beams, and also we're improving in the interface and the relation with the WIM, for interdata center connectivity, right? Also, we keep improving our installation experience. Now we have a more consistent experience for air-gapped environments, and that we are continuously refining in terms of documentation, but at least the functionality is there, and will facilitate more information on, and even troubleshooting cases when they arise. We can also install the new monitoring architecture and make, for the time being, we keep it optional, so it's not too much new information in one release. And also there's an automatic publication. This is mostly the part that you don't see, but it's what's happening behind the scenes to make your life easier. Is the publication of the chance for the channel-based installation for those who use that modality of installation, right? And also we have improved the OSM client with some refactoring of the commands to make them more easily maintainable, and also that could be extended. And now we can improve the documentation, the configuration of the beams for Prometheus-based telemetry. These features, I mean, it can be understood without the context of the rest of features that existed in the previous releases, right? So it's complicated to summarize features without this context. There are many slides like the one before that are making a summary of new features of the releases. You can get all the details on our release notes per release, by the way. And something that is worth noting, as you know, some releases ago we adopted a scheme of long-term support and short-term support releases. Air 13 as is even releases are long-term support, all releases are short-term, more intended for quick innovation and new addition of new features. Even releases are more for long-term stabilization, so you consolidate features in others and incorporate new features that we understand that are quite stable already. So this gives us the appropriate equilibrium between both type of needs and uses of OSM, right? And at this point, is very complicated to explain, as I said, in that context and all the use cases that you can cover with OSM, because they are, I would not say unlimited, but limited by our imagination and by in fact by the use cases that the OSM community or anyone in the OSM community has tested. Here we have some samples of the use cases that we have been showing in past OSM organized events, and others that are happening in private environments, and from which we obviously have information, but are not part of the things that are publicly available in OSM website and with the packages available in our in our repositories. But still, I mean, this gives us a good idea of what OSM can achieve, right? So, well, following with that spirit, we will continue showing by demonstration what we do in the new in the new releases. And for that reason, well, I would like to I would like to let the floor for Gerardo Garcia, who is the chair of OSM. I will tell you in detail all the details about the new closed loop architecture that comes with OSM Release 13. So over to you, Gerardo.
Thank you, Francisco Javier. Well, the idea is that we will introduce and we will give an overview of the new architecture for monitoring and closed loops that we have introduced in Release 13. We have done some steps in the direction of re-architecting the way we are doing monitoring and alerting and policies in general also. And we will show you an overview of the things that were introduced in this release and also a live demo. Okay. So first of all, why are we changing the architecture for monitoring and service assurance in general? Well, the fact is that there were some limitations with the current architecture. The current architecture was working. I will show you also that it's still available in Release 13. But we found some limitations that, and we thought that it was the right time to address them. So basically, there were some stages related to metric acquisition, normalization, evaluation of the metrics, etc., that were handled by a single container, which is not what the microservice architecture, let's say, suggests, right, that we should follow, right? A more distributed approach where we could have more individualized tasks being driven by different containers. Also, the scalability, that the workload was not properly served between the different Mon containers, and somehow there was some replication of the effort between the different containers also. It was, we have also found that in terms of code management, it was complicated to add new capabilities. It was possible, but it was, it requires some effort. And finally, something that it was also in the very beginning when we started with all the monitoring is that mostly all the things that were introduced in OSM had a primary focus on the visualization of the metrics, right? And we thought that it was good to give a redesign thinking on the actual use cases where an orchestrator is providing added value. That's mainly for doing closed loops like self-healing or auto-scaling, and being able also to incorporate alerting mechanisms. Okay, and that's something that it was not, let's say, in the spirit of the previous architecture, and probably that's the reason why we had those limitations. So with that in mind, we were analyzing different open source projects and different also architectures used in other contexts, right? And there is a well-known architecture that is followed for data analytics, that it's a kind of pipeline vision, okay? You could understand the pipeline like a set of stages, a set of steps where the output of each stage is used by the next stage in the process, right? So with that in mind, we thought that we should have an architecture that allows us to have different steps, different stages, focus only on a specific aspect related to metric or alerting. So for instance, metric acquisition could be a stage per se that is focused on acquiring metrics from an external source to OSM, right? Metric normalization could mean, let's say, the normalizing the metrics so that it is understandable and is useful for OSM. Okay, because well, maybe the concept of CPU or memory for an OpenStack private cloud might not be exactly the same as the resource consumption of CPU and memory in Azure, let's say. Finally, also, well, there are a set of stages, you have them here in a picture. This is the process that or the pipeline that we think that we should follow. Here by pipeline, we don't want to replicate, let's say, a data analytics pipeline. It's not the idea, but it's the concept behind that is what we understood that we could follow. So with that in mind, what we have done in this new architecture is try to identify different stages, and as each step can be done independently, what we have done is identify the data source or the input or the place from where the data come, let's say, and have a dedicated software for the process, and as output we will store the output of that process also in a database. So in general, we have something that we read from a database or system, and we have a process that analyzes that data, and in the end, it stores that also in a database or an internal database in OSM, right? This is a paradigm that it's called typically ETL in data analytics, and this is something that we have followed here. So the building blocks for the new architecture are mainly two: the Apache Airflow and the Prometheus stack. Prometheus was already part of OSM. Prometheus is a time series database. It's a database oriented to store time series of data. Okay, and well, it's well known in the open source ecosystem. And it includes also some additional components like Grafana for the visualization and Alert Manager for managing alerts and other components. And Apache Airflow is an Apache project, okay, from the Apache Foundation, that it's focused on or it provides a way to design workflows for mainly analyzing data in general, okay? And but in our case, we are using it to manage the workflows for the specific tasks in the monitoring pipeline. So just a quick summary of Apache Airflow and Prometheus. First of all, what's Apache Airflow? It's an open source project for workflow management. In general, it started as, it comes from Airbnb, and it became an Apache incubator project in 2016, and it is already a top level Apache software foundation project since 2019. Airflow is written in Python, and the workflows are created by Python scripts. And this is important because, as you know, most of the code, except in the UI in OSM, is based on Python. So we wanted to find a way to be able to build those workflows with Python. It has, the Apache Airflow has different components. When you deploy Apache Airflow, you have different components. First of all, you have a web server that is providing you a UI for managing the different workflows. You have also a scheduler that is in charge of scheduling, let's say, the different tasks to be run. The workers that are the actual runners of the task to be done, and the DAGs. The DAGs are the code that is the code that is modeling the task to be done, and it's follows it's a directed acyclic graph. It's a graph that has a beginning and an end, and it always goes in one direction without loops. Okay, that's what means directed acyclic graph. Okay, so more specifically, it seems that I don't know if we have missed the slides right now. They are loading again. Okay. The directed acyclic graph is basically is a collection of tasks. So you could see here some examples of the figures, right? You have a set of tasks, one after the other. The output of one task could be used by another task, and the output of the last task could also be stored. The DAGs are defined in Python. One thing that is important is that these graphs can be dynamically created. For instance, we could think of creating one per beam or one per network services. The task inside the DAG could also be created dynamically. This was important because it could allow us to scale pretty easily by having a different task per VM, for instance. And it's in general, this DAG is designed well to scale. The tasks are running in the Airflow workers, the runners, let's say, and they allow to run tasks in parallel. And one thing that is important is that each DAG could be scheduled independently. For instance, we could have a periodicity of 1 minute to get, let's say, VM status of an OpenStack private cloud, but maybe we don't want to, let's say, request or query public cloud so often, and we might think of different schedule interval for a public cloud. Okay, that could be an example. Okay. And Prometheus Stack. Well, Prometheus Stack could be well known by mostly everyone, but basically Prometheus is the database, the time series database that you have in the center of the picture right now of this slide. Prometheus pull metrics from other components. The components that from where Prometheus is pulling the metrics are called exporters. So we could have exporters for the different clouds, for Beam exporters, for VMware Beam or OpenStack Beam. We could have metrics from the BNFs that we could get with a BNF exporter from a BNF could expose some metrics that could be pulled by Prometheus. And also in some cases, when there is not an exporter, it's possible to rely on a push gateway that is could be an element that, in fact, we are incorporating in this new architecture to be able to so the element, let's say, will push the metrics to that push gateway, and we will get the metrics from that, and we will pull the metrics from there. We have the alert manager where it's to let's say manage the different alerts that are generated by the Prometheus time series database. We have Grafana, a visualization tool that could query metrics and present them in dashboards, and we have something that is internal to Prometheus is something that are the recording rules that allow you to create derived metrics from existing ones. Okay, this is pretty useful, and this is something that we have used in this new architecture. So what have we added to OSM Release 13? Well, first of all, we have included Apache Airflow and Prometheus. Well, Prometheus was already part, but we have included a Prometheus push gateway so that we could incorporate metrics from external sources easily. And we have added also Apache Airflow to manage the different workflows for instance, for the metric acquisition. And these are examples of metrics, the metrics that we have included in this release. So the acquired metrics are NS topology. Basically, we are getting from MongoDB the information, and we are pushing to Prometheus. And for that, we are using an Airflow DAG and Prometheus push gateway. The VM status, we are getting the information as a combination from Mongo and the cloud and the Beam, let's say, to and we are pushing that information to Prometheus. And for that, we are also using an Airflow DAG and the push gateway. And for the beam status, the same. Okay, we will see that in the demo, so I won't go into all the details. And so for that, we are using Airflow. And for the derived metrics, what we are doing is that we are getting metrics that exist already in Prometheus, and we are transforming them using Prometheus recording rules. So the process that is used to transform our metrics into new metrics is the Prometheus itself, using the concept of Prometheus recording rules. So, okay, these are some examples of the screenshots of the different Airflow graphs that we have, the DAGs that we have in Airflow, and also here would you have a screenshot of the new derived metrics, but we will see them for during the demo. So how to install this new architecture? Well, it's pretty simple. It's just you could install OSM with this option, NGSA, and it will install, in addition to OSM, it will install the new experimental framework for the moment. Okay, and what is installed when we are doing this? Basically, we're installing two Helm charts, Airflow and Push Gateway, and you could see here the pods that are being deployed with those Helm charts. This is coexisting with Mon and Pol. Mon and Pol are still there. And you could see, for instance, that in Prometheus configuration, the Prometheus is getting the metrics from two places, from the push gateway that is added with the new architecture, and the Mon exporter that is the previous existing one. Okay. Well, and now I think that it's time for the demo. Let me share my screen. I hope that you could see right now my screen. And well, let's first of all, let me go into OSM and check what you can see here. Okay, you see that we have already. Well, let's go. First of all, let me show you what we have right now in OSM. We have a beam account here. This is an OpenStack based beam. Okay, that was already added, and we have also an instance that is running in that beam. Okay, that was done for the purpose of making the demo much quicker. Okay, so we have already deployed a beam and a network service instance. Let's check what we can see in Prometheus. Well, first of all, this is Prometheus. Let me add the panel here. We could check, for instance, the metrics. These metrics existed before. For instance, we could see the status of the beam. Okay, this is the information that existed before the new architecture, so we have not changed that. Okay, in Grafana, you could see still the beam there. As always, the network services that were running in our project. Okay, this is something that existed and we have not changed at all. So what have we added? Well, we have added new metrics that have a different name but are following the same behavior as before, right? And we will be replacing some metrics by the others so as we move on in the new releases, right? So the equivalent metric right now that we are using is beam status for the beams. Okay, let me execute it, and you see here that we have here the beam status with a 1. I'm going to remove this panel so we are not getting confused. So let me show you the three metrics that we are acquiring in OSM right now. First of all, the beam status, DNS topology, and another one that is the VM status. Those are three new metrics that we are acquiring from OSM directly, right? And those metrics are actually acquired by Airflow DAGs, okay? So you will be able to connect to Airflow with the deployment. If you are able to deploy OSM with a new, and you deploy it with, or you install it with a new architecture, you will be able to connect to Airflow web server, and you could see here the different graphs that you have. So we have a graph, a workflow to get the NS topology. This is the workflow here. This is the UI of Airflow. It's not nothing that we have deployed with OSM. The DAX is what we have done in OSM. It's what we have developed. So we have the NS topology DAG. This NS topology is getting the topology from Mongo and pushing it into Prometheus. So we have it here, okay, NS topology. So what we have with the NS topology is one entry for each of the VMs. So in this case, let me show you, but if we go to the NS instances, we see that there is a network service. This network service consists of 1 and 2 VNFs, and for each VNF, we have 2 VMs. So one network service with 2 VNFs and 2 VNFs with 2 virtual machines. So a total of 4 virtual machines. That's the reason why we have here 4 entries. For each virtual machine, we have 1 entry and the status that it's 1. Okay, that's what we could see here. We have also, this is the NS topology graph that it's acquiring the NS topology metric. We have also the beam status. The beam status is basically getting the status of the beam. And we could see it here that there is a beam. So the status is 1. And the beam status, let me show you here, it's also a beam status that is getting the status of all the VMs running in a beam. So for instance, let me show you right now, this is the beam that we are monitoring. This is an OpenStack. It has 17 virtual machines. So we should see here 17 entries in our Prometheus, right? We have the 17 virtual machines with status 1 because they are running, okay? So that's what we are acquiring from OSM. This is, and the acquisition is done with this Airflow DAGs, okay? So that's the first step. We have seen that it's useful to get metrics from the beams or the NS topology or the beam status or the beam status using Airflow DAGs. In other cases, we might find that it's more useful to use exporters, and that's the freedom that we have, right? In the end, what is important for us is that the metric that is acquired lands in Prometheus so that we could use it, right? So how do we use these metrics? Well, we are, let's say, combining these metrics together to generate more useful metrics. And that's why we are using here the rules. We have here 3 rules: VM status extended, PNF status, and NS status, that allows us to create these new metrics, and we will see the actual output of that. So VM status provides us all the VMs in a VM, but VM status extended is combining the information of the NS topology with the VM status and providing us only the status of the VMs that are running in a network service, and extended with all the labels corresponding to the network service ID and the VNF ID. So we have here the whole information, right? And now let me remove the previous panel so that we are not getting confused. This is the first derived metric. And based on this metric here, we are getting the actual VNF status and the network service status. So we see that there are 2 VNFs that are running, state 1, because all its VMs are running, and we have a network service that is also running. It's worth to mention that this is done okay, automatically from the previous acquired metrics, and it's done automatically by Prometheus using those recording rules, which saves a lot of development effort, as you could imagine, okay? And we are getting these indicators based on the previous one. Okay, so, well, this is the way we are deriving the metrics. Let me go back to the slides for a second. So we have seen the components that we have installed. We have seen Apache Airflow. We have seen the instantiation of our first network service and the metrics acquired and derived with this new metric. Let's do the following. Let's add a new beam, a new beam account, okay, and deploy a network service there, okay? So that's what we are going to do. So first of all, we are going to, let me share my screen again. Okay, we have right now a single beam for the moment, and we are going to add a second beam. It's a Google Cloud account, Okay, and that's what we are going to add right now. So let me check if it was properly added here, and it's enabled, so it's added, and we are going to deploy a network service there. So we are going to deploy a more simple network service, a basic network service consisting of a single VM, a single VNF with a single VM, okay? And we are going to deploy it, okay? This is done. Let's go right now to, well, first of all, let's check here in the OSM GUI that we have added. We have our second VM, GCP, Google Cloud Platform, and we have our instance here, NS instance, that is being deployed in Google Cloud, okay? And we will see it in Google Cloud right now in a moment. So what's interesting here is that the new VM and the new instance that were created, well, there will be new metrics that are dynamically generated. So first of all, we could see here, these were the DAGs that we had previously. We had a graph to get a workflow to get DNS topology, a workflow to get the VM status, and a workflow to get a VM status. So what we could see here right now is that after adding the new VM, we have 2 extra DAGs that were added, okay? This here is a new DAG to get the Google Cloud Platform status, the status of the VM GCP. And this one here is the graph to get the status of the VMs running in Google Cloud Platform. These two are new. You could see here that, well, this was executed only twice, 2 times, okay? So we could see here, go here and see the executions, okay? The first execution, the second execution. This is being run every 2 minutes or every minute, it seems, okay? So you could see here, and you could go to a specific execution and see what happened in the log, if if it was okay or not. Yes, VM status, true, it's okay. Well, so those DAGs here were automatically added by OSM, okay? That's the one of the good features of Airflow is that allows you to add dynamically these DAGs, okay? And well, since these DAGs are already collecting metrics, we could see the metrics in Prometheus, right? So we could, first of all, see here that we are going to see only the derived metrics probably because it makes, we could see all the metrics, okay, but maybe it makes sense. We had previously 4 VMs with a status of 1, okay. Let's execute it again and we will see that we have a new VM, okay, corresponding to the new network service. What about the VNF status? We have a new VNF, right? So we should have another VNF with its status to 1. Right now it's -1 because for the moment it's not yet ready. Let's go to the console of Google Cloud to see the status here. Let me rephrase. This is the new one, HF Basic. It's in Europe West. This is the zone. By the way, I should filter by zone so that we don't see the others, okay? Because this is the only one that we have added when we added the VM. Okay, so right now it's working. So since the VM is right now up and running, probably if I refresh here, we should see the VM as working, or at least in 1 minute or so, we should see it as working. Okay, let's wait a little bit. It will have to refresh it, that information, and we will see that the VM is available. Let me add another one here, another panel. VM status. This is the acquired metric. We have, this is the VM from the VM ID. This is the VM ID of Google Cloud that we have just added, and this is the VM ID. Still not ready for us. Let's wait a little bit. Well, in addition, the metric of the VNF status is obviously reflecting the same status, okay? And the same here. but it's reflected as not yet working. Okay, let's see if we have it. As soon as the metric is properly here and it's properly captured, it should be derived here. Meanwhile, I think it could be useful to show you the status of the things that are running here. You could see that, Helm in the namespace OSM and see that Airflow and Pulse Gateway are running here. And we could also see the pods that are running. We could see that we have Airflow here running and Pulse Gateway also running. Let me check here the status. Okay, just to the back what's going on. I will go to the VM status here. Check the VM status for each VM. Here, 7 times what I achieve. Let's go to one of the executions and let's see the metrics that we are getting. Reading beam info, ID, YAML load. Well, there seems to be here a warning, but nothing wrong. This is the machine that we are getting. This is the ID that we should have. Return value was known, so probably we are doing something wrong here and we are not getting the status because there is something not working, and that's the reason why it's reflecting -1. So, well, I will have to check that's what happens with live demo. But in general, you could see that the metrics are once the metric is derived, let's say, it's somehow translated to the appropriate derived metric. Okay. Well, so that's basically what I would like to show about the new architecture. Just to end up, I would like to comment what are the next steps regarding the new architecture, right? First of all, the main idea is that the MON and POL functionality will be gradually transferred to this new architecture. And this means that in a midterm, we will probably get rid of MON and POL and we'll have all the functionality covered with Airflow DAGs and Prometheus recording rules and exporters, probably. The work items that we are working on involve different stages. First of all, the metric acquisition. We will evaluate different exporters to get metrics to be able to be scraped by our Prometheus, and also dedicated Airflow tags when there is no Prometheus exporter. We will use that to get for instance, the resource consumption in the beams and case clusters. Also, the exporters could be used to get the metrics from the network functions. And we could also use DAGs, for instance, to get the status of the SDN controller or the case cluster status. The alerting. Right now, the alerts are being generated by MON. Our idea is that we will generate ourselves the alerts for failed VMs and failed networks based on the metrics that we are getting. And we could also incorporate webhooks or alert webhooks from the network functions. The closed loops that we have today with auto-healing with MON and POL for the auto-healing, auto-scaling will have to be managed by a different procedure in this case. In the end, calling again, doing similar things, but we're following this new architecture. And finally, the presentation of the different metrics, the BNF status, NS status, BIM status, etc., will be possible through the graphical interface and the OSM client. And that's all related to the new service architecture. Next point in the agenda is the demo of the enhanced management of persistent volumes. Mark,
Thank you very much, Gerardo.
Okay, you can proceed with that. Thank you very much.
All right, thank you very much, Gerardo. Welcome to this short little demo on the enhanced management of persistent volumes. In OpenStack, there are a number of different ways of being able to persist data or have your VMs have disks that they can write to. There are two main services. One is Glance, which is images that are usually used for ephemeral things. So if you were to boot your VM using a Glance image, when you delete that VM, the Glance, like the local copy of the data goes away and it's all released. They also have volumes in OpenStack. Now, volumes aren't local to the VM. They're typically deployed over something like Cinder, where it's a distributed storage. Sorry, it is backed by Cinder, but implemented by something like Ceph, which is distributed storage in the background. So what we're going to be talking about is how OSM is capable of interacting with OpenStack for these different types of storage devices. So in the very basic configuration, OSM can deploy a VNF. That VNF would be represented by one or more VMs. And that VM would end up getting an image from Glance, using that as its root disk, starting up. And once we terminate the network service, OSM will go in and remove the VNF, which also tells OpenStack, go ahead and delete anything that was associated with it, because it's all ephemeral storage. So what we'd like to do is talk now about the enhancement that was there. Inside of the descriptor itself, we have a section for virtual storage. And there we can specify types of storage that we want to use. The first one that I'm going to do will be the root volume. So what that means is we're instructing OpenStack not to use an ephemeral, local Glance storage for the root disk, but to actually create a volume in Cinder and boot from that volume. That volume can be persistent, which means that it will live on, or OSM can delete it when we're done. In this particular case, we're just saying, okay, we want a persistent storage of 10 gig. And then next I say, okay, I'm going to create a volume with the ID of persistent storage. It's going to be 1 gigabyte in size. And here is where we get the new keys. So you're able to specify storage requirements through to OSM to know how to handle the back end. And in this case here, we've just added a simple keep volume flag, which can be set to true. And that indicates to OSM, as part of the cleanup, do not delete the volume when we're done. So that is what we're going to be showing. And lastly, you can also specify a type of ephemeral storage, which is a way of saying, yeah, we do want to use a local Glance, QCOW image on the hypervisor, and OpenStack will automatically take care of the cleanup of that. So I'm just going to be showing a little bit about how each type of persistent storage works. So let me just start our little demo here. So what we're going to show here is first, we're going to show what's available in OpenStack. So first, from an OSM perspective, I have already created a virtual infrastructure management entry for my OpenStack. I show in OpenStack that I've got no servers available, and there are no volumes available in OpenStack. So brand new clean tenant within OpenStack, and we have our OSM packages loaded. As an aside, the packages can be found in the OSM packages Git repository under the OSM GitLab setup. So now we're going to create our network service. We've got our NSD name. That's the NSD that we're using. The Vim account that it's going on. specify a little bit of configuration, wanted it attached to a network called OSM EXT, and gave it my SSH key so that I can log into that VM. So what did that do? That created VNF, which is represented by one VM. It created a root volume in OpenStack with the operating system. Base Ubuntu is all we're doing here, but the base operating system, and it's going to boot that. And it also created a persistent volume. So, and it will be attached to the VNF itself. So what does that look like? We go in under OSM NS list. We can see that our network service has been instantiated. When we go into OpenStack, we can see, there's the VM associated with it. And when we take a look at our volumes, we can see that there are 2 volumes that have been created, and both of them are in use, which means they are attached to our VM. You can see the attached to right there in the volume list. And lastly, when we do the OSM VNF list, on the very end, we can see an IP address, and that's the IP address of our VNF's VM, so we can interact with it. So we are going to log into that VM and take a little bit of a look around. Just log in here. Okay, so we're inside the VM now, and we can see that the root volume VDA has been mounted on /. Great, that works fine. And our ephemeral storage shows up under /mnt. Okay, we can write some data to it. This file won't be persisted, and we put it into /mount/ephemeral text. And it is present. So the next thing that we're going to do is we're going to attempt to mount the volume that was created. Of course, that doesn't work because OpenStack just created a volume but didn't initialize it or anything. So we format it to a file system. Now we can mount it, and we can put some content into that mount point that we created, /data. So the volume has been mounted, and we have put some data into it. Next, we're going to terminate the network service. And if you recall from the earlier slide I showed, everything was deleted. But this time, because of the flag that we sent to OSM, it will not delete that one volume that we asked to keep persistent. So we can go ahead and delete the network service. That's done. And now we can see in OpenStack, there are no servers left. And if I go in and take a look at the volumes, I can see the volume is still there, and it is now available and not attached to anything. Great, our data is there. So now how do we use that volume so that we can see our data again? And remember, this persistent volume is now available in OpenStack. So we could do something like have one network service that uses the volume to create data. And then once that's done, we can terminate that network service and start another network service to consume that data. So it doesn't have to be the same network service. If you want to attach anything to an existing volume, doesn't matter if it was created by OSM or not, you can attach any existing volume to your VNFs now via OSM. So what does that look like? OSM deploys the VNF. It asks for a root volume, attaches it to the VM that starts up, and attaches to the existing persistent volume. So let's go ahead and see what that looks like. First, we have to find out the volume ID. There it is, beginning with DCB. Then we do an ns-create command. And this time, you can see that not only am I saying, oh, map the management network to my actual network name, but I'm also specifying a little bit of additional information here. I am saying that I want you to override the keep persistent volume VM entry inside of the VNF descriptor and add a volume ID to it. So this is how we can specify what volumes to use at network service deployment time. You just simply say, oh, please use this volume ID. And that volume ID must already exist in OpenStack, or, well, we'll get a nice error back from OSM saying, sorry, we're unable to start your network service. You've asked for a volume that doesn't exist. Okay, so what does that look like? New network service has been created. It's ready, it's idle, it's up and running. If we take a look at the volume list, you can see actually that both are attached again and attached to the device. And when we log in, we can then do the same things. Examine the root volume, okay. It's mounted under / again. We can see our ephemeral storage. And remember, we had written something to ephemeral storage before, but it's not there anymore because, well, it disappears when you delete the VM. So let's go ahead and mount the persisted volume. You'll notice this time around, I didn't need to format it because it's already formatted and has data in it. And when we mount it and take a look at the data, we can see, yep, hello from the OSM 13 webinar. That was us. That was the data we put in there. Now, and sorry, that is it. So let me return to our slides here. And we can go ahead then and open the floor for questions. Actually, sorry, I'll turn it back over to Claire for a moment to give us a little update.
Yeah, thank you. Thank you all. Yes, we have a couple of questions now and just a few minutes left. So let me see. We have, the first one is there more documentation about our gap installation procedure? Who wants to take that one?
I will take that one, Claire. So no, I have just checked the documentation of the OSM user guide. That it's where the documentation is located. Let me share my screen, and there is it's not documented there, the procedure for the air gap installation, but the procedure for air gap installation, if it's basically an automated procedure where OSM is taking care, the installer is taking care of the installation so that you don't need to worry, okay? So the main idea behind the air gap installation is that if you are in an environment that is connected to the internet through a web proxy, and you have already configured that machine, that machine to be behind a proxy with HTTP proxy environment variables and these kind of things, OSM will detect that and will do the appropriate configuration of the machine to be able to work in that environment. Okay. But good point for the person who asked, because it's not right now in the user guide. Okay, it's not yet there, and we will take that action point and we will make sure that this information is properly in the documented user guide.
Okay, we have another question now. How to get persistent volume ID from OSM without accessing OpenStack console API, sorry.
That is a very good question. And unfortunately, I don't have the answer to that right in front of me right now. But how can we follow up on questions, Claire, so that I can ensure we get that one addressed?
We can send an answer to the person by email, so don't worry, we can do that.
Perfect. Thank you very much. My apologies for not having that information ready.
Yeah, just a comment, okay, because I think that we will check that offline, Mark, but in general, all the information about the resources being used by OSM is part of the NS record or the BNS record. So information like the VM IDs, network IDs, interface IDs, volume IDs are stored as part of the BNF record and DNS record in general. So I guess that's where the information will be available, okay? But anyway, we will check, as Mark was saying, okay?
Thank you. Okay, the last question now, because time is running out. Can you specify the difference between non-kept persistent volumes and ephemeral volumes? It seemed to me both just disappear when the VNF is terminated.
Absolutely, I can take that question. So the difference between the two of them is an OpenStack difference. In OpenStack, there are the two different types of storage. One, which is what ephemeral falls under, is controlled by glance. And what happens there is when the hypervisor starts up your VM, it's going to use the local file system of the hypervisor it's on for its ephemeral storage. So the data that's being read and written is just being kept inside of a local file on the VM. And if you migrate the VM, obviously that's going to be migrated to the next server with it. Volumes, on the other hand, are stored in Cinder. And that has its own separate life cycle independent of the VM. So when you create a volume, what you're doing is you're actually creating like a disk in Cinder, which would then be backed by something like a distributed storage like Ceph. And so if you migrate the VM from one hypervisor to another, the data doesn't need to move because it's a networked file system that is being used for your disk. So the fact that OSM automatically cleans up the volumes that are created makes it look like there is no real difference between ephemeral storage and volumes. However, with the addition of this flag now, we can really make a distinction between the two of them. And you can say, okay, I would like a persistent volume, or I want to reuse an existing volume. That is not possible with glance and ephemeral storage. You cannot reuse anything from glance unless it's the full base image that boots the VM. So any changes that were made in something that's based off glance will never be persisted, but volumes can be. I hope that explains the question.
Yeah, thank you, Mark. I'm afraid time is running out, so we'll answer the other questions by email. Thank you all for attending this webinar, and of course for our three speakers today. And remember, keep an eye on our ETSI Brighter channel as we're making webinars on a regular basis. Once again, thank you and goodbye.